So during the time, it took up to 3 million years for this to happen. Extinction was a little bit up, but speciation was way down. Lots of species invasions going on, and a huge amount in ecosystem restructuring. So kind of all of the key elements that we were interested in being useful for looking at species invasions. All right, now you're all familiar with the Devonian period. What we're going to deal with, of course, is the late Devonian. The mass extinction interval happens here, between the Fronian and the Fomenian stages. Now, in the Devonian, when we're talking about biostratigraphy, when we really want to understand intervals finely, we use conodonts as our biostratigraphic indicators. And so over here on the left, on the right, you see the conodont zonation. Now, you don't need to know these names, but I will be using these names on slides, so I want you to know what they mean. Basically, these are just placeholders. These intervals represent time periods ranging between 1/3 to 1/2 million years in duration. So we're going to be looking at things over very short time scales for when we're dealing with the Paleozoic. I'm going to start here, back in the Gavation, and this basically is the Penn-Dixie quarry levels, for those of you here or going there later. So basically we're dealing with those type of taxa, and then we're going to move up through time. Now the extinction interval is here. And so we're going to be looking at before and after it, so we can kind of see what we should expect during the regular time, and then what happens as we move through the crisis.
Conodonts are worms.
Now, one of the things that does happen is that in the Middle Devonian, every different region across the globe had a very specific fauna with very endemic species. So the species of the Michigan Basin look different than those over in New York. By the time we get to the late Devonian, into the Fronian, all of that breaks down. And we start to see the taxa looking very similar across many basins. Again, this will be due largely to species invasion, so we'll come back to how that worked. To remind you what the globe looked like, this was the time of the Acadian orogeny. We're starting to compile Pangea together, and so we've got mountain building going on right here on the east coast. That's going to give us a great foreland basin with lots of sedimentation right through here in New York, and all around this area. We'll talk a lot about those rocks. Okay, now when you have mountain building on the edge of the continent, some things happen in the middle of the continent also because of that. So when you apply a huge amount of force at the edges, mountains go up, and right behind the mountains, the foreland basin works down. Further into the continent, you have additional upwarping at the edge, of course, in your peripheral bulge. And so depending on whether you have loading or quiescence, or basically quietness, at the edge of on the mountainside will determine what's going on with these arches in the middle of the continent. So if there's loading, then the arches will work down. If there's no loading at the edge, then the arches will bounce up. And so this is going to be one of the mechanisms that we talk about for how species can actually cross between the different barriers that existed here in North America. Part of it's going to have to do with what's going on with the mountains on the coast. Okay, now my research is multifaceted. I take a kind of a multidisciplinary approach to attacking questions. So the 3 prongs that we're going to deal with tonight are biogeography, which is simply where species occur. So for example, when you're looking at your bird book, there's always that map of where every species lives. That's what we're going to be dealing with the fossil record. Secondly, we're going to be dealing with ecology. The reason every species has a range is because it has specific environmental tolerances. We're going to be trying to understand what environments different species live in. And all of that, of course, will tie back into evolution. When you have new species forming, this is basically an ecological process of breaking up an old species range. Secondly, extinction, of course, is simply just when there's no habitable environment left and the species goes extinct. So our focus taxon will be the vastly wonderful and superior brachiopods. The reason we're dealing with brachiopods, you can probably pick this up already. To do this type of thing where we're looking at range mapping, we're going to have very abundant taxa. As you guys know very well, brachiopods are ridiculously common. Because of that, they're a perfect taxon for this type of analysis. While things like trilobites lived in these rocks and they were beautiful, they're just not abundant enough to answer these types of questions. So we're going to be looking at wonderful brachiopods. Okay, so let's talk about how we do these. Okay, well first of all, of museum collections. So I went to about 15 different museum collections, looked at all of their Devonian brachiopods for this time period, re-identified them myself, because, you know, the person that identified them in 1920 used a different species definition than I did, so everything has to be re-identified. From those collections, you can get a couple things: species ID, the location, and the stratigraphic unit that those particular species came from. So just to give you a sense of the data, that's kind of how it plays out in terms of spatial extent. Here's where all the different species live. We're going to be focusing on North America. The two yellow circles indicate areas where I went out into the field and collected some new fossils because the museums didn't have very good data. Okay, now, to map our species, we're going to take a pretty straightforward approach to start with. You're going to take all the data that you have and you're going to put it onto a modern globe. We're going to use a program or a package called Geographic Information Systems. This is a mapping program, it's a computer-based mapping program that's used in all kinds of disciplines, but this is actually the first time it's been used in paleontology. But I hope you see it's really useful by the time we get done with tonight's talk. Okay, so you map your points, and then you rotate those back into paleocontinental positions. So you rotate this, and here you can see our nice brachiopods now are living in the appropriate locations. Now, you're all very smart people, so you also notice that there are less dots on this rotated map than on the first one. The reason is because this map on the right is for a single time slice. So these are only the brachiopod occurrences for that time slice, whereas the other ones were for the entire data set. Okay, so I made a separate reconstruction for each of those 19 conodont zones we talked about, all the way through this interval. And then for each of these maps, I took the data points for each of the species in the data set and drew a polygon around them to enclose the range. So this is the range of a sporiferid brachiopod during one time slice. I did this for 341 species of brachiopods and bivalves. Basically everything in the database that's common enough to do this. In the Devonian, bivalves basically live along the sandy shoreline. Brachiopods live everywhere else. So this gives us a range all the way from the front of the delta out into the basin. Okay, and then you just can calculate the area. One of the great things about computerized mapping is you've got a lot of spatial tools. And so here, this is the range of this particular species. Okay, now we can do this through time, and this is Schizophoria, and you guys will probably see this one. This is a very common orthid brachiopod. But what we can do is actually kind of animate how its range changes as we move through these 19 time slices. So here you can see its range is kind of expanding here. Now it's going to invade Iowa. As we move into the extinction, it kind of goes away, and then it comes back as a Lazarus taxon. So basically, we can do this for all 340 species in the database, which is a lot of fun. And I'm not going to show you all of their videos. But what I am going to do is tell you, based on all this type of data, so what? I mean, what kind of scientific questions can we then address? We're going to look at three things. What's the relationship of the size of species ranges to what's going on with sea level? How do these relate to these invasions, moving in between these basins? That's really what we're trying to ask about. And then how does this relate to survival through the crisis interval? All right, so here's the relationship. Here's sea level. This is a sea level curve for this time period. And here's what's going on with the average species range. You can see that it basically tracks sea level at a very broad scale. If we do some statistical analysis, and I really don't want to bore you with this, but what I do want to tell you is that, yeah, what we see is a very strong correlation. So species ranges are changing in concert with sea level. And in fact, we see that species ranges increase as we go from a nearshore environment off to an open shelf environment. Now, so we see these changes in range with environment, we see these changes in range through time. So the question is, if you've got a big range, is this going to help you get across the invasion interval? And in fact, yes. Yes, it does. So species with big ranges are crossing the crisis interval. Those that are victims, those that go extinct, have much smaller ranges than those that survive through this interval. We can also compare this against survival. I'm sorry, I can't get rid of stats tables. I tried really hard, but this is the best I can do for getting rid of the numbers. But here's the point of this one. It turns out that if you guys remember way back to when you took, 9th grade biology or college biology, you would have learned about a thing called a chi-square test. And